we see the case 1 in which the pedestrian is jaywalking. This is the view from the buggy in which the camera is mounted. Here we see that the pedestrian is jaywalking and only the lower body is visible. Still the camera detects the pedestrian and stops. This is from another angle. Here is the side view of the pedestrian jaywalking, and we see when it comes in the range of the car's camera module, it stops automatically. And when the pedestrian leaves, the car moves. Here is the case 2. Pedestrian suddenly appears in front of the car. In this case, we will see a pedestrian immediately coming in front of the car. For example, a kid playing with an aeroplane. Here we see the kid immediately comes in front and moves, and the car still stops before colliding. Here is another angle. Here we see the child immediately comes in front of the car, but the car still detects it and stops. The third case, pedestrian under reasonable occlusion. In this case, we will see the pedestrian has been occluded by some bags and jacket. Still, the model is able to detect it and stop when he was passing by. Here we see the pedestrian is occluded by two different bags, and still the model was able to detect the person and stop. And the car moves again after he crosses his path. Now we see the case 4, pedestrian under heavy occlusion. In this case, the pedestrian is heavily occluded. Nothing is visible, but still the car detects the pedestrian and stops. Here we see the pedestrian is heavily occluded by jackets in his upper as well as lower body. And the car moves again. Thank you.
Hello everyone, my name is Kunal Madan of Computer Engineering. Today I'd like to share insights into our project's foundational steps that lay the groundwork for the future of autonomous driving systems. Our journey began with the EuroCity Persons Dataset, a treasure trove containing annotations for pedestrians across various European countries. But before we could train our YOLO V5 model, our dataset underwent a crucial transformation. We meticulously cleaned it, pruning redundancies and ensuring alignment with our model's requirements. Now, to boost our dataset's diversity and robustness, we applied cutting-edge data augmentation techniques. Picture this, resizing images to a standard 640 by 640 pixel format, random rotations to prepare for pedestrians from varying angles, and even adding simulation blurriness or noise. These techniques enhance our model's adaptability to real-world scenarios. But let's rewind a bit. How did we get here? It all started with gathering diverse data, real world driving scenarios, simulated environments, a myriad of road conditions, traffic densities, and weather variations. Once collected, we had to pre process this data, cleaning it up, normalizing, and augmenting it to create a well rounded dataset. Now, onto the tools and technologies that fuel our project's innovation. Python, a versatile language, became our primary tool for its extensive machine learning capabilities. TensorFlow and OpenCV served as our guiding lights, providing powerful frameworks for deep learning and aiding image processing tasks. Additionally, the Raspberry Pi platform stood as the backbone, interfacing seamlessly with our hardware components like the motor controller and camera module. In just a glimpse, you have seen how the fusion of data collection, meticulous cleaning, advanced augmentation, as well as cutting edge tools lays the groundwork for our autonomous driving pursuit. Thank you.
Good morning, everyone. This is Pranay Malhotra. Our diverse ECP dataset, which was augmented using the ImageAug library, was trained using transfer learning on a YOLO V5 model. A set of very important hyperparameters such as learning rate and epochs were used to provide the best results possible. We made a major of two optimizations on our model in order to get the best deployment possible on the Raspberry Pi. The Raspberry Pi is unable to work with a very heavy model such as YOLO V5. Hence, we needed to convert it into a TF Lite model, which is much lighter than the YOLO V5 PyTorch based model and uses the int8 quantization. The intricate quantization enables it to reduce the size of the weights and boost our FPS from below 1 FPS to up to 9 FPS. The second problem that we faced in our model was that initially we wanted to use a stereo camera setup. However, using two cameras required twice the amount of data usage and hence twice the amount of processing. The Raspberry Pi was unable to deal with so much data, and hence we had to shift to a monocular depth estimation model, which was based on using the widths of the detected objects. This slide tells us the performance parameters that were used to assess the performance of a model. The first performance parameter was the box loss error, which is of two cases, the train box loss error and the validation box loss error. As we can see for the train one, that as the number of epochs increases, there's a steady decline in the box loss error. Same can be observed for the validation box loss error. Next parameter that was used was the mean average precision at IOU to 0.5. The MAP is a metric that combines precision and recall across different confidence thresholds. The MAP 0.5 specifically calculates the average precision at an intersection over union threshold of 0.5. The next parameter is the recall. The recall is the ratio of true positive predictions to the true actual positives, indicating the model's ability to capture all relevant instances in the dataset.
My name is Priyansh Agarwal, and I worked on the hardware implementation and integration module. So here is a final product, the buggy. So I will tear it down one by one and explain you all the components and all the connections. So basically, first we attach the motors, 4 motors we have here. So we soldered all the wires, positive terminal and negative terminal. Similarly, for all the motors, we did that. Now, all the wires we got on the top of the plate, and then one by one we connected it with the L298N dual motor bridge controller. So how it is working is like, first we have a 12-volt battery that is powering this driver control motor module, and then this power is then being transmitted to all the motors accordingly as we have coded it in our program. So these are the GPIO pins of the Raspberry Pi here, and all these GPIO pins are connected with one input in motor module. So we have here 4 modules, as you can see. So each 4 inputs correspond to the 4 outputs here. A pair of outputs correspond to left side of the motors, and a pair of outputs correspond to right side of the motor. So basically, when we give high signal to the 29th pin of the GPIO in the Raspberry Pi, so the right wheels move forward. Similarly, if we give high signal to the 33rd pin of the Raspberry Pi, the right wheels move backward. And if we give high signal to the 31st pin of the Raspberry Pi, then left wheels move forward. And similarly, if we give to the 32nd pin of the GPIO in Raspberry Pi, the left wheels move backward. So here are the connections. We have used the red wire from the 12-volt battery here to power in the 12-volt socket of the L298N motor module to power it on. And similarly, we have used the ground also from here. And we have also used the ground of Raspberry Pi in the motor module. And then we are using the camera module that is here, the upper plate. We have a camera module here, the Logitech C270 webcam, and we have a power bank to power the Raspberry Pi. So basically, this Logitech's USB serial port is connected in the back of the Raspberry Pi here, and it is then used, and then the video feed from this camera is used in the program to detect the pedestrians. So first, we have imported the RPI GPIO module that is being used to interface with the Raspberry Pi. So first we have initialized 29th, 31st, 32nd, and 33rd pin as GPIO.out so that we can send signals out from the Raspberry Pi to the motor module. First, we have the function that is init function. In this, we have defined 2 tuples, one tuple for left wheel and one tuple for the right side of the motor of the buggy. So the right tuple contains both the values of the that correspond to the forward movement of the wheels and the backward movements of the wheel. And similarly, the left wheel tuple contains 2 pins that correspond to the forward and backward movements of the left wheel. So whenever we have to move the buggy forward, we have to move both the left side wheel and right side wheels together. So here we have turned the value true of the right wheel forward and left wheel forward. And when we have to stop the buggy, we have to turn off all the pins so that no current is being passed to the motor and the motor stops working. So we turn all the functions, that is L wheel F, R wheel F, L wheel back, and right wheel back to false so that the motor stops working.
Hello everyone, my name is Panchu Saxena and I'm going to walk you through the code of how our pedestrian detection model actually works on the buggy. So first of all, in this file detect.py is where the magic happens. Firstly, we can see normal import libraries of CV2 and time, and then we can see from tflight_support.task import core, processor, and vision. These files help us to run our tflight model, which was converted from PyTorch based model because the Raspberry Pi could not handle the heaviness of the TensorFlow of the PyTorch model. So we had to convert it to get appropriate frame rates for appropriate detection of pedestrians. Now we can see we chose 4 threads for we ran multiple iterations in which we found that 4 threads gave us the maximum FPS. The display width and height are given as follows: 960 and 540, and RI is the instance of object robot which was present in the code of robo.py, which was explained by Priyansh earlier. Now in this code we set the height and width of the frame which will be going to be appear on the screen when the model actually runs. Now in this code we can see the positions and the height and weight of the output screen has been set, and these lines of code are for the TensorFlow model. Now this whole part of the code is for the while loop, which continuously runs again and again and takes the image feedback from the robot sensor. And in this code we can see person detections. This is actually the object which detects the person and tells the model that if person is detected or not. And xmin, xmax, ymin, ymax are the bounding boxes positions which will be detected by the model. Here we can calculate the width, and we use we use this function to create the bounding box on the screen. And this distance is the variable which calculates the distance based on the formula that distance is always inversely proportional to the width of the pedestrian. Now we can see that in this part of the code we use the q key to quit when we want to stop the model, and this part calculates the FPS in real time. Thank you.